Good morning, everyone. Today is the last day of our workshop. So today the first speaker is Professor Donghui Jeong of Penn State University. The title is Cosmic Birefringence Mediated by Dark U1. So let's welcome the speaker.
Hello. Thank you everyone for inviting me to give a talk here. So my talk is, as Donghan said, Cosmic Birefringence mediated by dark U1. So as you can imagine from the title, I'll tell you about the birefringence signal, which example of which is here. And then I'll tell you what it is in a second. But unlike the conventional wisdom that birefringence is mediated by some pseudoscalar, so I'll tell you another story that the birefringence may be mediated by the dark sectors birefringence. And then in this case, what are the general consequences of that mediated birefringence? Okay. From last summer up until last April, I stayed in Kiev during my sabbatical. So I was very fortunate to interact with many people, but I was particularly pleased to interact with the young scholars, such as Sungmuk Lee here. He is a grad student in Yonsei University, and Dr. Dongwoo Kang, he is the postdoc in Kiev, and all those seniors. So these two people were the leading working force underlying this project. So if you have something you like about my talk, this all done by these two. And if you have something that you don't like about my talk, it's all my fault, okay? So let's get started from the birefringence signal. So birefringence happens for the crystal if there's a crystal that doesn't have a fully symmetric structure, and that crystal can have different reflective index depending on the polarization state, okay? And this example shows that, I mean, in the piece of paper, we have 5 English letters shown: island, and star, and the calcite, and double reflection. And this material here, I think is a calcite, the 방해석 in Korean. And then that material is birefringent material. So you can see that the double reflective signal in this letter, star, and then ND, and then CA, right? And this figure is coming from this gemrockoptions.com, and this is not 100% accurate because it depicts as if the straight line, the vertical instant light is reflected. But other than that, this has a good explanation, so I brought it here. So let's think about the case where we have unpolarized light incident from the left to right and passing a birefringent material, and it's reflected. But then, because this material is birefringent, so the reflective index is different depending on the polarization. You have horizontal polarization passing through like this way, and the vertical polarization is reflected this way. As a result, we see the double image of this one letter, right? That's called the birefringence. And then cosmic birefringence is referring to a similar phenomena, but not with a linear polarization, but with a circular polarization. So let me explain the cosmic birefringence. This has been studied from the 70s in this paper. The setting here is that we have a pseudoscalar field, such as an axion field, that couples the photon by the Chern-Simons term, like this one, okay? And then, I mean, this term is F mu and F mu, and theta field here is the pseudoscalar field, and then GA is the coupling. And if you use the simple integration by part and use the Bianchi identity, and then you can rewrite this Chern-Simons term as this form. And you have A mu, the vector potential, and multiply with this minus coupling constant times gradient, the 4-dimensional gradient of theta times F tilde. And then we can reinterpret these terms as a current, and then you can just rewrite the Maxwell's equation, replacing rho and J with this 4 current, right? So this is a new set of Maxwell's equation, right? This usual Bianchi identity, and then this one is these two are the equation with the source term. And then if you combine them, and then you can form a usual wave type equation, right? The left-hand side and right-hand side is usually 0 in the vacuum. But now we are thinking about the universe filled with a pseudo-scalar. The right-hand side now contains very symmetric structure with a coupling constant and theta dot and time derivative, and then grad theta dot grad. So that's basically the inner product between partial mu theta and then partial mu of E field and B field. Okay, and if you have this, here the assumption is that we assume that this G coupling constant is small, and then theta, which is cosmological scale field, is varying much slower than the E field and B field, whose wavelength is about, say, I mean, it's very microscopic scale, right? It's like a couple of 100 to million angstrom, right? And if you solve this, if you solve the plane wave equation, you can get a dispersion relation. And in this case, the dispersion relation for the right-handed polarization mode and the left-handed polarization mode are different. Okay, so this is a modified dispersion relation. So W omega square plus minus refers to right-handed or left-handed polarization mode. And then if you can take the square, we have this. The right-handed and left-handed photon has different phase velocity. Okay, so that is the outcome of introducing this Chern-Simon interaction to the usual Maxwell-Lagrange. Okay. The summary is that if you have this term, the Chern-Simon's term, then we have phase velocity, the dispersion relation, different dispersion relation depending on the polarization mode, and then right-hand side mode and the right polarization mode and left polarization mode moving with different phase velocity means that if you have linearly polarized light somewhere in the universe, and then the polarization angle of this linear polarization is rotating with a rate given by the integration of the pseudo-scalar field along the path length. Okay. So where do you have this linearly polarized light? Obvious answer is in CMB, and the CMB is far away in the cosmological distance, and we have enough distance to integrate this quantity. So that's the perfect candidate to look for the cosmic birefringence. Okay, so this is a schematic diagram of summary. So here, here is the picture shows the cosmic microwave background at the time of recombination or decoupling of photon from the electron. And then we have this pattern around the cold spot and the hot spot. We have this linear polarization pattern. And then along the way, if the photon is passing through a universe filled with a pseudo-scalar field, then each and every linear polarization is rotated by the constant angle given by 1/2 GA times integration of B eta theta prime. So we expect to see this shifted pattern on the sky. Okay. So yeah, as I said, we normally see this pattern of the temperature anisotropy, and then you can also have the pattern of the polarization of CMB. So this is a polarization of CMB as a line plotted on top of the temperature map, smoothed with a 5-degree filter. Okay, the CMB is polarized because this map that we are seeing is a result of Thomson scattering at redshift 1000, or the CMB's decoupling time. Okay, so this reason is simple. So if you have this picture is from the Wayne Hoos website. If you have unpolarized natural light coming from the left and then bouncing off, and then the Thomson scattering means that you this incident electric field is accelerating the electron, and then that generates the radiation, right? So in this case, the vertical polarization doesn't do anything, but then horizontal polarization will move the electron left and right to generate this linearly polarized light. Okay. The same thing is here. So if you have instant light from the left to the center, this is an electron at the last scattering surface. But then this electron is scattered up and down because the left and right directional shake that cannot make the light coming toward us. So if you look at this diagram, you must think that here and there, this plane is on the surface of last scattering, and then the photons are coming from the left, right, up and down to escape along this direction. We are here. Okay. So the polarization signal depends on the local anisotropy around the electron at the time of last scattering. So for example, if electron is surrounded by isotropic radiation field, but then the polarization here comes up and down and backward and forward, and here left and right, and then backward and forward. And of course, backward and forward doesn't do anything. And what affects the net polarization that we observe is this one and that one, right? But then if they have the same amplitude, same intensity, and we will not have any net polarization. It's unpolarized light. So if electron is surrounded by isotropic photon field, it will not generate any polarization. So polarization can be generated if electron is surrounded by anisotropic photon field, such as this. So we have the left instant photon has large intensity, which is depicted by blue, and then photon coming from up has small intensity depicted by red. Okay. As I said, the only two polarization modes that affect our net polarization, observed net polarization, is this one and that one, right? So as a result, we have light from both polarization plane, but then up and down polarization is much bigger than the left and right polarization. So we will have a linearly polarized light. It says quadrupolar anisotropy because you have to imagine that the same photon coming from the bottom up with the red and right to left with blue. Okay, so if the electron is surrounded by quadruple anisotropy, then we see the net polarization. That's why compared to temperature anisotropy, the polarization amplitude is much smaller because it requires quadruple and higher order anisotropy at the time of decoupling or the time of the last scattering. Okay, and this is the pattern of CMB polarization around the peak of temperature anisotropy. Okay, so this again, the left hand side is measurement of from the Planck satellite. The red spot is the hot spot in temperature anisotropy. Blue is cold spot in the temperature anisotropy. You can see that the polarization pattern has very strong correlation with the temperature anisotropy. Okay, it is because of the requirement of quadruple anisotropy that I mentioned before. So if you pick only a hot spot and the cold spot and then stack them together, and you can see even better pattern. And this is what they show here, that they show in the Planck paper, Planck 2018 paper. You see that this is I think stacked around the hot spot, I think. And then we have this first ring with very cold spot, cold ring, and the third ring is very hot ring. So temperature is hotter than the surrounding and the colder than the surrounding. Okay, and then when the temperature is cold and the polarization pattern is tangential to this annulus, and the temperature is hot, polarization pattern is radial to this annulus, right? You can make sense of it if you think about this in terms of the quadruple scattering that the GIF that I showed you before, right? Because I mean, if you think about in terms of electrons sitting right there, okay, for this electron, from the up and down, we have higher intensity photon coming and scattered here and then coming toward us. And then left and right is colder, the low intensity photon coming and then scattered to coming toward us, right? In that case, the dominant intensity polarization will be parallel to the higher intensity of photon. Okay, that's why we have this pattern. So the rule of thumb is that if the temperature, the polarization generated from the temperature anisotropy is always parallel to the direction of hot photon. Okay, I hope that makes sense. Right, and then this pattern, that the polarization pattern generated from the temperature has one characteristic. If you reflect this whole pattern with a mirror, and it will go back to itself. It's called the parity-even part of polarization, okay, or E-mode polarization. So in Fourier space, we define it systematically in this way. So if you have in two-dimensional Fourier space, instead of K, we write L, the harmonic multiple. Then if L goes from left to right, if the polarization mode, polarization direction is either parallel to the L or perpendicular to the L, we call this E mode. Or if the polarization angle is 45-degree inclined in both way, left and right, we call them B mode. And if you define this way, E mode is parity even and B mode is parity odd. Because if you reflect this whole picture to the mirror, you get this. And the E mode will reflect it to the same E mode, but B mode has changing its inclination angle. That means that B mode will change sign from positive to negative. Okay. And if our universe has no parity breaking interaction for the CMB, the only non-zero correlation that we expect is all parity even, like E square or B square or T times E. Those three are the only non-zero correlation we expect in the universe without any parity violation. Okay, and if you have
Donghui, can I jump in there? There were some recent papers on parity violation in large scale structure. There was at least two. There was one by Oliver Philcox and another by a group out of Florida.
Yeah, I'll tell you about it.
And they seem to be claiming that this could be a primordial. It had to be primordial. It had to be like something to do with inflation.
I don't know if it has to be.
but you're assuming that basically there's no parity violation at the CMB, right? Is this what you're assuming?
I'm saying if. Okay. I think I will show you a tentative or tantalizing evidence that CMB might, they might also see the parity violation in the CMB.
Okay, thanks.
Great, yeah. So, is it call game?
Okay. Yeah, Owen.
Yeah, Owen, yeah. So, as Owen said, as I said, if parity is conserved, then this must be the case. But if somehow we have some interaction that violate the parity, just like the cosmic birefringence signal that I mentioned before, then we expect to have this parity odd signal like T times B or E times B. Okay, and then that signal is called cosmic birefringence. Okay, so in this picture, as I said, this one and this one, they are obviously parity even part, the E mode polarization. But if you shift, if you rotate the polarization angle by a constant amount, and you end up having this signal and that signal, that is in fact a combination of parity even part and parity odd part. Okay, so even though the statement is that even though we only start in the early universe from the even parity, okay, correlation, by rotating each polarization angle by constant amount, we can generate parity odd part. right? And then that signal will be most apparent in the cross correlation between E mode and B mode polarization. And that's what these people did. In Askilt and Komatsu paper that came out like last May, 2 months ago, they have studied the E mode and B mode cross correlation signal from the Planck and W map. And they found this signal, okay? That's the raw data. And then their biggest worry here is that we are talking about the rotating the polarization angle by a constant amount. What if we miscalibrate the polarimeter that we installed in Planck and WMAP by a constant angle? Here we are talking about very, very, very tiny shift. I mean, the measurement here, their measured cosmic birefringence is about 0.3 degree. That level of accuracy is very hard to maintain. So what if we have that? So in this paper, Askilt and Komatsu paper, they invented a new way to calibrate, self-calibrate this instrument alignment. And then they have claimed that they have detected this cosmic birefringence to 3.6 sigma significance. Okay, so it seems like there's something is there. Okay, something is there, and there's some indication that this EV cross correlation might be there. Although this significance is only 3.6 sigma, this can be an important check. Okay, and also they have measured this cosmic birefringence signal at different frequency band. Oh, by the way, for I think the past 6 slides, or the 5 slides, I shamelessly copied the slides from my physics advisor, Komatsu. So, but I don't think he minds. Anyway, I have to say that the source of this slide is from him. That they also measure the cosmic birefringence signal as a function of frequency, and the frequency dependence seems to be consistent with a constant, almost constant. But this one, although it cannot guarantee that this stays constant, right? But it can rule out one other possibility. If the intergalactic medium from the last scattering surface to us were filled by strong magnetic field, we know that there must be a parallel rotation, right? The linear polarization angle in the magnetic field is rotating, okay? And then this parallel rotation, however, has very strong frequency dependence, the nu to the n, 1 over nu square. I mean, this is much milder than 1 over nu square. So this signal that they have detected cannot be the Faraday rotation. Okay. And I mean, they haven't claimed the big detection yet, but this 3.6 sigma, that can be important, right? And then if we are to interpret this correctly, I think we also have to explore other possibilities that can generate the same signal. Okay. So here comes our work. So we have studied other possibilities by employing the coupling between the CMB photon and dark photon. And this paper is in preparation. Yeah.
Donghui?
Yeah.
So
please.
regarding the Komatsu's recent results. So I mean, what's the difference between the? I guess he had another observation from the maybe nanograde last year. So regarding the parity-violation signal from the sky, what's the difference from that result?
I mean the nanograph?
Yeah. So I
oh, I see. So I think that one is from the gravitational waves.
Right.
And I think they haven't claimed the detection yet, if I understand correctly.
No, at that time it's more or less about 3 sigma. So right.
So if I mean I don't know the details, but if I mean my educated guess is that what they may claim is the parity violation between right-handed and left-handed gravitational waves.
Right.
because that's what nanograph is sensitive to.
Right.
And this one is the parity violation that we observe from the right-handed and left-handed, the CMB photon. So they might not come from the same origin, but if you have some parity violating stuff filling the universe, we may see the same result of the same effect.
Right. So at that time, they also claimed some kind of axion effect. Right. Okay.
Right. I mean, naturally, if you are to generate the differential phase velocity between the right-hand side and left-hand side, you need some pseudo scalar, because then you need to couple some scalar with differently right-hand and left-hand side. So I think it's natural that people invoke axion for that kind of physics. Yes.
But with Donghui, if we go back to basically the parity asymmetry in the large scale structure that is claimed to be there, wouldn't this sort of tell you that it's probably not an axion?
I don't know.
You know, if that's so, it's very.
Okay.
It's kind of interesting that we do like these observations could easily be connected. I don't know.
Right,
The others are about high 2 sigmas, maybe 3 sigma-ish.
Oh no, it's 7 sigma.
which is what do you mean?
Let me, because I think you're interested. I'll tell you. I'll jump in and I'll show you this slide. So what they did, like in the past
this
month,
is the paper, Hu and Wilcox, right?
Yeah. Right. Then Wilcox paper, and then there's a Jiaomin Hu paper. And then what they did was they have measured the 4-point function of galaxies. Okay. And because the 4-point function of galaxy is the lowest order n-point function that is sensitive to parity if the universe is rotationally invariant. If you think about the triangle, right? If you think about the triangle, the 3-point function, and then do the parity inversion, you can get the same triangle by rotating the original triangle. But if you have this one like the tetrahedron, and if you have parity inversion of tetrahedron, you cannot obtain the same tetrahedron by rotating the original tetrahedron, right? So that's the reason why there's no. I mean, the 4-point function, the tetrahedron, is the lowest order n-point function sensitive to parity violation. And then what they claim in this paper, the Ho et al., they said from the both galaxies, they have detected 3.1 sigma and 7.1 sigma, depending on the
I missed the 7.1, right? But yeah, that does look suspicious, right?
But then the Wilcox paper with the same sample, CMS sample, he claimed that it's not 7.1 sigma, it's 2.9 sigma. I mean, this is very hard exercise because you're talking about the 4-point function, and if you are to correctly characterize the uncertainty, you have to quantify the 8-point function, right? So I mean, it's very hard to quantify. I mean, I can believe that there's something there, but
yeah, I think it's probably
the uncertainty is hard.
So just connected to this, there is some work by various people that they look at, spins in galaxies and how they're oriented on the sky, right? And in principle, this could be connected as well. There's anomalies there.
That's true.
So and also, just getting back, if this is real, then it probably says that this is not cosmic birefringence. Is that what it says?
No, I think, I mean, if you have the axion field, and then the axion field is, say, dark matter field, right? And then if you have dark matter,
could you get this parity? Could you get this parity violation in large scale structure from an axion? That's the question.
Right, but I don't think there's. I mean, it can be, right? Right. Requires that you have one field that cares right-handed and left-handed differently.
And it changes the orientations of galaxies, right?
Right. So I think
actually, and I had another question, which was basically related to the 3.6 sigma, right? They started off at 2.4. The improvements are combining WMAP and Planck, but what else?
Right.
So it's going from 2.4 to 3.6 is quite substantial. So can you explain what the improvements were?
I think having WMAP and Planck, they have Okay, I think if I read correctly, in this most recent one, so and as I said, one of the biggest worry is the miscalibration angle, right? But then by having many different mode of observation, they sort of randomize the miscalibration angle, right? So they added E and EB cross correlation from various two different instruments, but then the instrumentational misalignment has added, right? But then it seems to me that this WMAP and Planck were misaligned in different way that they will cancel. So I think that'll increase the significance.
So I can see what's going on here. People make a 2.4 sigma claim that's conservative, and then you go start looking for, how do I get those extra sigmas? And you can find them, right? You can find WMAP and Planck, and then maybe you increase your sky coverage as well. But
right, they increase sky coverage too, yeah.
Right, and then you're kind of stuck at 3.6 sigma because I guess we're waiting on how else, how could you go further?
There's other the polarization experiment like CMB stage 4 or the Simons Observatory, and we can also measure the same thing from those experiments.
Right, on patches, right?
Right, yes. Yeah. Okay. All right, so enough about the birefringence and the parity violation, and we have new ways of generating the same thing from the mixing. So if you have standard model photon, that's F mu nu, and then dark photon, X mu nu, that can be mixed by this way. Then you have some coefficient chi and F mu nu and X mu nu, and to be general, I included also the mass term, and then the standard model current and the dark current. And then we have diagonalized this one to pin down the real photon and real dark photon, right? The first case we think about is the case where we have massive dark photons, right? In that case, to satisfy the fact that our standard model photon is massless, we have to set this mixing angle to 0. By the way, this theta is not axion, it's an angle, the mixing angle here, okay? But then the interaction term becomes this. So we have standard model coupling, and then dark photon couples to standard model current and the dark current, okay? And this was very severely constrained. And then also the standard model photon doesn't couple the dark photon directly. So there we don't expect to see the birefringence signal from this case. So we move on to the massless photon case. In this case, two photon field, the standard model and dark photon field are both massless, and then they enjoy the full symmetry. But then the conventional way of setting this mixing angle is setting sine theta to chi, and then cosine theta to square root of 1 minus chi square, and then this interaction term becomes this. So we have dark photon coupled to dark current, then standard model photon coupled to standard model current and dark current. Okay, and this coupling is constrained by many experiments, including the lab and LHC. So we have this constraint plot as a function of the mass of fermion and then the interaction strength. Okay, you have supernova constraint, and then you have lab and LHC. And this region in parameter space is very interesting. That is where the standard model fermion mass is GeV to TeV range. Okay, and I'll come back to you why it is interesting later if I have more time. And if you think about this massless photon case, we have coupled Maxwell's equation. So now Maxwell's equation has two components, the standard model photon and dark photon, okay, and it's dual. And standard model photon coupled to the dark current as well, with this epsilon parameter, this Milli-charge, okay. And then we solve this equation by defining this A prime, which is A minus epsilon times X mu. In this case, this equation system can be simplified by just look just like the usual Maxwell's equation, but with a further A prime field. And then we solve this equation and then solve the propagation of the electric field that describes this photon with two parameters. First one is alpha. Alpha is the difference between phase of standard model photon and then dark photon at the time of CMB's decoupling. and beta dm is the cosmic birefringence of dark photon since the decoupling time up until now. Okay, the dark photon is initially misaligned by alpha and then rotate by beta times dm. The details of how we calculate this thing is not quite important for this analysis, but we have these 2 degrees of freedom. That's important. Okay, so the electric field solution we obtain by solving the Maxwell's equation is following. So if dark photon, as I said, is propagating to z direction with amplitude a of k, and then has initial misalignment angle alpha, and then from the decoupling time to now, it has rotated more further by beta dm. Okay, and then on the other hand, electric field, the standard model E field, has amplitude of b of k and propagate along the z direction. Okay, and then has this extra term proportional to the Milli-charge and r of k, which is a ratio between dark photon to standard model photon. Okay, so if you have this E field, electric field, amplitude and phase, we can first calculate the induced birefringence. Okay, so standard model birefringence is related to these parameters, alpha and beta dm, and epsilon, the Milli-charge, r, the ratio between the dark photon amplitude and then the standard model photon amplitude. Okay, so good. We can induce some birefringence, but it turns out that we don't have complete freedom because we not only generate the phase shift, we also generate the shift in the rotation angle. We also generate amplitude, right? So the amplitude of CMB after it is affected by the mixing between dark photon and CMB photon is given by this. So B of K was the amplitude of CMB at the time of recombination or time of decoupling. Because of the strong interaction, we expect the CMB photon follows the Planck function, the black body spectrum at recombination. But even though CMB photon follows black body, because of this kinetic mixing, we expect to have some deviation from the black body, which is very, very strongly constrained by the Kobe-Feiras observation. In this fixed error paper, 1996, their conclusion is that at all frequency from 60 to 600 gigahertz, this delta I over I, the fractional difference of CMB intensity compared to black body must stay less than 10 to negative 5. It's a strong constraint you can put in these parameters. Okay, that's why I said that it doesn't matter the details of parameter, but because they will be strongly constrained. But if I have now one equation, the standard model, the birefringence as a function of epsilon, r, and alpha and beta, and then spectral distortion as a function of same parameter. If I divide these two, I get one constraint equation of alpha and beta with this 5 10 to the negative 5 coming from the Kobe-Feiras constraint that CMB must be black body. And then if I plot this thing as a function of beta, and this is the reasoning parameter space, that is possible, depending on the allowed standard model birefringence generated in this way, okay? So for this analysis, I think the converging point is that alpha is 2 alpha is minus beta. That's the converging point. And this is a condition where the spectral distortion is exactly 0. And then we guarantee that CMB is a black body. Okay. So for the later analysis, we just fix this value to this relation. Okay. So for the black body CMB, the birefringence is given by this simple form. It's a 2 times epsilon, which is a Milli-charge. R is the ratio between 2 intensity, CMB intensity to the dark photon intensity, and then sine times dark photon, the rotation angle. Okay. So up to this point, this R is a completely free function. But to make the progress, we assume that the dark photon, just like a CMB photon, is also thermalized because of some coupling that dark photon can enjoy, right? And then it decouples. Okay, so we have two temperatures here: the CMB temperature TCMB and dark photon temperature and TDM. And then the fact that birefringence is proportional to R, which is a ratio between these two electric fields, which is given by the ratio between two black-body functions, that gives us another very strong constraint. Okay, it is because the black-body function has a Rayleigh Jeans region and then Wien tail. Okay, but the important fact is that beta SM is constrained by the observation. These data points are the same data point I showed you when I said this observed birefringence does not seem to show very strong the frequency dependence, right? So if the dark photon temperature is much greater or much lower, much smaller compared to CMB temperature, then we must see the sudden dropout or sudden increase of standard model birefringence because of the difference, because of suppression in the Wien tail. But we don't seem to see those suppression here. So that gives very, very strong constraint on R. Okay, so here the Sungmook plotted 5 different values of R from 0.2, 0.3, 0.4, 0.5, 0.6. You can see that 0.6 already drops to 0. I think, but this guy happened to have large error bars, so that might make it best fitting value. But still, we see that 0.2 is not fitting very well these data points, right? So that is basically the reason why you can constrain the temperature of dark photon from this observation. Namely, we cannot see the Wien tail or the peak of the Planck curve anywhere in this frequency range. So this is the final constraint that we obtain. So left-hand side is the R is the ratio between the dark photon temperature to CMB temperature, and y-axis is this function, the epsilon times sine function. This is 1 sigma and 2 sigma contour. And then if you marginalize over this PDF, we get the marginalized PDF for the R, the ratio between the dark photon temperature in unit of CMB temperature. So this is using our method, cosmic birefringence. So if we are to explain 0.3 degree from the photon mixing, okay, and that is required temperature range, right? But then we don't have complete freedom for that because we cannot increase dark photon temperature arbitrarily high, because there's a measurement from the CMB or NBBN about the number called N effective. This is the effective relativistic neutrino degree of freedom. So these include all the relativistic particles that exist in the universe, okay? And then this value has error about 0.17, sanctuary value of 2.99, and then we can turn this thing into the PDF of R, the dark temperature ratio, and this is a semi-prior consistent with this number, including this dot point at 0. The 0 means that we don't have any dark photon degree of freedom. That's also possible. And then if you multiply these two, then you got the prior and with the posterior distribution of dark temperature with CMB prior. And if we are to explain this observed birefringence from the photon mixing, and then the dark photon temperature must be within this range. Okay, so 1 sigma lower bound is 0.3, so which means that dark photon must be at least hotter than the 0.8 Kelvin. That's very solid prediction of this model. Okay, so let me conclude the so far, and then we have tantalizing evidence, observational evidence of 3.6 sigma significance detection of EB cross correlation. Okay, if this comes from the axion FF dual coupling, this can tell us something about the pseudoscalar field that can be dark energy if it's homogeneous, or dark matter if it's clumping. And we also, but the alternative explanation that we found is that birefringence can be a signature of kinetic mixing between the standard model photon and dark photon. Okay, and then in this case, dark photon must satisfy first spectral distortions. You cannot spoil the beautiful black body spectrum of CMB, and second, and temperature must exceed 0.84 Kelvin. So that's the prediction of this theory. If we are to explain the birefringence, I think this is a very strong conclusion from such a simple theory. So I really like that, because it means that we can rule out this theory at some point. And let me come back to this constraint plot. And I said this is a very interesting reason. The reason is because of this statement. So Chandrasekhar mass, okay, is the maximum mass that star, like white dwarf, can hold up against its gravity. Okay.
5 minutes left.
Yep, I have like only 3 slides. And this Chandrasekhar mass is related to the Planck mass, which is a fundamental constant over the proton mass, cubic times proton mass. And then that winds up being 1 solar mass. Okay? And then Planck mass, we all know that it's fundamental constant, but the proton mass, on the other hand, could be anything. It's just determined by the QCD, right? What if we have some dark matter fermion, which is heavier than 1 GeV? And then if you have something like a stellar evolution that we have right now, and then the implication is that Chandrasekhar mass for the dark particle that is heavier than GeV, just like in this region, right, can be much smaller because it's inversely proportional to the square, right? That means that, I mean, when people talk about the mass gap in the gravitational waves, that's the mass gap between the heaviest neutron star mass and then the lightest observed black hole mass, right? And then that mass gap is give and take some other unit number is of order of magnitude of Chandrasekhar mass. Okay, so if we have dark sector fermion that's heavier than the proton mass 1 GeV, then which means that we can generate many subsolar mass black holes. Okay, well, that was the motivation. And then with LIGO people, like LIGO Bodo Kagura people, myself and Sarah Sendera are working together in searching for the subsolar mass black hole and its possible interpretation of dark matter physics and then primordial black hole physics. We still haven't found the conclusive evidence for the subsolar mass black hole, even though we have a couple of triggers. But so far the story is that we can constrain the fraction of dark matter black hole in the dark matter, okay, from the LIGO data. And we are keep decreasing this far, and we keep searching for this subsolar mass range by looking at the gravitational wave data. Okay, and also dark photon in this context is very important because dark photon is the energy carrier to carry out the kinetic energy of dark matter particle, so that the dark matter particle can collapse to form compact object. Okay, so dark photon has very interesting phenomenology and very far-reaching implication of dark matter physics and like gravitational wave source and the CMB Parity-violation. Thank you very much.
Thank you very much for very interesting talk. So, any questions?
I have questions. Yeah. So
yes.
Yeah.
Please.
So in the conclusion, you mentioned about the dark energy effect of dark photon. So can you tell about some more details about that? For example, what's the equation of state of the dark photon, and then it's.
Oh, I think that depends on the potential of this axion field, right? I mean, we do not know the axion field, but I mean the fact that we have some pseudoscalar that generate this kind of cosmic birefringence means that you can use that scalar to do something interesting, right? I mean, this is the first time, if this turns out to be true, it's the first time that we found new pseudoscalar, so you can use it for dark energy and dark matter. But I think the crucial difference is that dark energy must be smooth over the entire universe, but dark matter must collapse in clumps to make the large scale structure. So those are the differences.
Right, Donghui, if I can add to that, I would sort of say that this only makes sense as early dark energy, right? Because of the biasing in local H0 determinations. So it can't be, you know, it can't be a traditional dark energy quintessence type field in the late universe. It would have to, it has to change basically the BAO scale to be viable. I mean, it's fine. You can work these things together, but it really has to be an early universe. It has to affect that BAO scale.
Well, why are you saying so? Because to solve H0 tension, is that?
Right. I mean, basically, if we don't change the BAO scale, so, you know, then we're stuck at 67, right? It's very difficult to go away from 60.
Yeah. Yes. But I think more important thing is that to make a new scalar field to have dark energy model, right? I mean that this Hubble tension might be solved by some dynamical dark energy that may have something to do with the dynamics of theta, right?
But it's very easy to prove. Like if you start from lambda and an equation of state that's W equals -1, and if you take any mock data that's consistent with Planck lambda CDM, you can prove that if you go above W equals -1 into the traditional quintessence or effective field theory regime, that H0 goes in the wrong direction. H0 goes to lower values. And this is just very simple analytics. It's just an analytic argument. So
you're saying that dynamical dark energy cannot solve the H0 tension. Is that what you're saying?
If it's in the W of Z greater than -1, it makes it worse. Not that it can't solve it, it just makes it worse, right?
Okay. Yeah. That makes sense.
Okay, so I think our lead. Yeah, okay. Yeah. Oh, I have a question though.
Yes.
Sorry, I have a question. The frequency dependence is very interesting, right? In this cosmic birefringence. If we can go back to the plot. I mean, this data point at 353 is something else, right?
Oh, right. That's right. It rotates to the opposite direction. Yes.
Right. So this whole thing is driven by, I guess 44 you can more or less eliminate. Then you've got, like, it's not clear to me that this is a constant, right? You know, it could be a constant, but it could also be.
But I think one big motivation for this plot is that you can exclude the Faraday rotation, right? But of course, as I showed in this plot, I mean, it doesn't have to be constant, and we can have some slope.
Right. Yeah, this was interesting.
It with other, yeah.
Yeah, this is certainly interesting. Okay, thanks.
Okay, so because the time being, so let's thanks to speaker again.
Thank you for your attention.
And the next